All right, so let's finish the last type of integration that I want you to look at. And so that is integrating when we're using arc trig functions. Sometimes I think these are the trickiest to recognize, and sometimes I don't think about them until after I've tried other things and I've become a little desperate and I'll go, wait a minute, is that an arc tangent problem? So remember, we know the derivative of arc tangent x is 1 over x squared plus 1, or you could write it 1 over 1 plus x squared. So the antiderivative of 1 over x squared plus 1 is arc tangent x, and of course plus c, okay? Do you recognize this one? The derivative of which arc trig function gives you 1 over the square root of 1 minus x squared? I sure hope you're thinking arc sine x. And then, of course, plus c. So this is the unusual guy. That's the one that gives us arc secant x plus c. Now, I'll tell you that in integration, you're more likely to see these. So we're going to focus on those in more complex problems. You may see this, but I think if you did, it would be almost identical just like that. I don't think that they would give you weird u-substitution problems with them. So these are similar problems, and we won't do both, but I want you to recognize that both of these are almost x squared plus 1 or 1 minus x squared. The 5 on top's a non-issue because the 5 on top can always be pulled to the outside. So that's sort of a distractor. If you write the problems like that, then they really look closer to the original formats. All right. So on this one, on these two problems, let's work this one just so you see how this works. All right. So to work a problem like this, and sorry, I'm having a hard time getting the board to focus as well, the camera to focus. I know that I want this to be x squared plus 1. So what I need to do is factor out the 100. So if I factor out the 100, I would have to say, well, it's x squared over 100 plus 1. Okay, that's the first thing. Now, this 100 can come out. So now I've got 5 over 100. It can come outside of the integral. And I've got 1 over. Now, let's write the x squared over 100 as x over 10 squared plus 1. Well, if I say let u equal the x over 10, or 1/10 x, then this integral immediately becomes 5 over 100. Tell you what, instead of writing 5 over 100, let's go ahead and make it 1/20th. The x over 10 becomes your u squared. So we've got to figure out what do we do with the dx part, because I don't want the dx over here. I want it in terms of u's. So du equals just 1/10 dx. That means the dx will get replaced with, multiply by 10 du. Now, as you know, what would be more common for me is to say 10 du. That's the way I would normally handle it. So now I can see that this fraction is just 1/2. This is arctangent u. And I've gone a little off the screen here, haven't I? And so I'm going to finish up and say arctangent u was 1/10 x plus c. So not only is it sometimes hard to recognize, oh, that's one of those problems, and I just got us all out of focus, didn't the numbers, you have to be really careful about bringing those numbers out. Now, these two problems are also similar. And remember, I'm circling around the structures for arc tangent x and arc sine x. I think that would be more common than for you to have to do a lot of u-substitution with arc secant x. But these are the same kind of thing where instead of just x squared, I've got 16x squared embedded. So let's do this one, and then I want to say a word about this one here. So on this one, I know that what I want is for this to be in the format 1 minus u squared, or the square root of 1 minus u squared, because then I know I would say, oh, okay, so that's arc sine u plus c. All right, so I have to go, no, wait a minute, for this to be a good substitution, I need to say my 16x squared needs to be replaced with a u squared, which means that I need to look at 16x squared as 4x quantity squared, which now helps me get more clear that my 4x is actually what my u is supposed to be. Why is it necessary for you to get that clear on it? Because now you need to look at what is du. So the derivative here is going to be 4 dx. So when I'm trying to replace this dx, now I can say, so the dx has to be 1/4 du. So I'm going to make it like that. Now I'm ready to just say, okay, that's 1/4 arc sine u. How about I go ahead and plug in my u plus c? Because I mentioned to you yesterday that if you want to start skipping the u part and going ahead and inserting your x's, that's an appropriate place to skip your work. So this one maybe is a little easier. There's not so much number stuff that you need to be aware of. But let me mention this one, okay? You've had all kinds of fraction problems, and what we're going to do tomorrow is work on recognizing, well, on this kind of fraction, how do you think through what method you use? But then on this fraction that looks really, really similar, why does the method you use change? So this is definitely bottom heavy. If it's a top heavy or a balanced fraction, I tend to think, oh, top heavy fractions tend to be division. You do the long division first. Balanced fractions can be division or sort of that funky u-substitution thing. But when they're bottom heavy, that gets a little trickier. So this will not factor. I can't do anything with factoring. And my first idea is to go, oh, it's one where I'll let u be the bottom, so that when I integrate, I'll have a logarithm in my answer. The problem is that when you take the derivative, you get what, 32x and then dx. So I could say, well, the 1 plus 16x squared is my u, but then if I try to replace the dx, I get du over, look here, I get du over 32x. Well, I can pull the 32 out on the bottom, and I've got du, but I've still got this 1 over x term, and I cannot move forward if I have u's and x's after the integral sign. So I get to this and go, oh my gosh. And then I think, whoa, what might be one of those wild, funky u problems. So then I look back at my u and say, well, if I did u minus 1, that would give me 16x squared. U minus 1 over 16 gives me x squared. So I could say x equals the square root of u minus 1 over 16. So x equals the square root of u minus 1 all over 4. So then if I try to put that in here, oh, I know. 1 over means flip. So if I flip this, it's going to give me 4 over the square root of u minus 1. So I can bring the 4 out. But I don't know if you're recognizing, but this thing seems to be getting worse and worse. Now, I think probably on this one, there is one thing that we could do once I get to this point. We may be able to do a second round of u-substitution and maybe say m equals u minus 1, maybe. But this thing's not getting better. I feel like I'm working and working and working and I'm not getting anywhere. So when I've got a bottom heavy fraction and I start making my normal moves of letting u be the bottom, if I'm not getting anywhere, usually what happens is I start to have a little panic and go, oh my gosh, I don't know what's going on with this problem. And there are some problems in your book in this section that actually are Calc 2 problems, because you're going to learn some more extensive substitutions and some other algebraic things you can do, including what's called partial fraction decomposition. So I'm going to obviously not give you those. But if you have one like this, I'm giving it to you. That means I've already figured out it's not a Calc 2 problem. It's one you ought to be able to do. Well, one thing that I've noticed that helps me is, do you see that the degree of the top is 0, because this is technically x to the 0 term, and the degree of the bottom is 2. I have learned that when my degree of the top and bottom, if it's not like 2 and 1 or 1 and 0, if they're not just 1 degree separated, then that's a lot of times a trigger for me to go, wait a minute, is this a arc trig problem? And that's when I start thinking, oh, I could make this 1 plus u squared if I let u squared equal 16x squared, which means u is just 4x. And the derivative of 4x is just 4 dx. And then I start making progress. So if the derivative's just numerical, then it means that you can work with it. So I know that was a long explanation, but typically what happens is people will start to panic before they start to remember arc trig functions. That's the key. So these two problems are again similar, but now I'm throwing in some trig work. Do you see, for instance, on this one, I'm going to start with this one, but we'll actually finish this one out. But on this one, your immediate reaction might be to say, let me just let u be the bottom. When I do that, though, and I say, well, what's the derivative of the sine squared x? Because the derivative of the one part's just 0. But the derivative here is 2 times sine x to the first power times the derivative of sine x. And that immediately ought to give you pause, because you ought to be able to tell, I can make the 1 plus sine squared x u. The cosine x dx, I know how to replace. If I try to replace the cosine x dx, I get du over 2 sine x. And if I do that, again, it seems like I've got the issue because it's not immediately obvious what to do with the 2 sine x. All right. So whenever you feel like, oh, I did the du part and the x part of what's left over, there's not a good fit, unless it's one of those sort of funky u problems where you kind of keep pushing. It's usually an indicator that you're doing things wrong. And remember, on the funky u problems, the u part tended to be linear, and here the u part's quadratic. So I'm not saying there's no way it's a funky u problem, but usually if you get something like this, there's something going on. And if you don't see a pretty quick fix, so if I said, well, let me replace the sine x, because the 2 I can just move out here as 1/2. Well, the sine x, if I wanted to find it, I would wind up having to do the square root of u minus 1. And if you start having to insert more radicals, oh, you've got some issues going there. So this again is where you say, well, what if instead of letting u be 1 plus sine squared x, what if I let it just be sine x? Because I know the derivative of the sine x is the cosine x dx part. Well, if you do that, 1 plus sine squared becomes 1 plus u squared. And the cosine squared x dx part becomes the du. So I'll do 1 du. You can write du up here, but I don't like that as much. So I like writing 1 du. That makes me feel more comfortable. And now you see you got it in the arc tangent u format. So the same thing's true here. If you let u be sine x and du be the cosine x dx, then I can quickly see that on the bottom, I can get the 1 minus u squared format, and the cosine x dx part becomes my du. And now I've got the arc sine of u format. All right, so the last two problems, I'm going to focus more on the arctan because I think they sneak in on you. I think in the arc sine, the square root might be more of a trigger for you to at least think about arc sine. But I think the ones like this, I don't think you would necessarily go, oh, that has something to do with arctan, because it looks like a pretty simple problem. So x over 1 plus x to the fourth is what that says if you're having a hard time reading. So on this one, I'm going to start out and go, oh yeah, I know this one. It's bottom heavy. If it's bottom heavy, I'm going to let u be the bottom because I'm expecting I'm going to do the antiderivative and get an answer with a logarithm in it. But when I do du, I'm going to get 4x cubed dx. Now right there, I basically know I've got an issue because, again, the bottom's u. I've still got x dx. Let's suppose I try to replace the dx only. I'll leave the x here. Dx, I'll say, is du over 4x cubed. Well, then I'll have 1 over u, and I'll have du over x and 4x cubed. I can reduce to 4x squared. Okay, so I'm thinking, all right, I'm going to make that better. Well, look, I still have this x squared, and it's not obvious to me what to do. And I might consider the funky u thing, and I could say, well, this is u minus 1 equals x to the fourth. And if I took the square root of both sides, I could say u minus 1 is x squared. And then I could say, well, that would be the square root of u minus 1. But again, it doesn't necessarily look like this is getting better. If this was u and u squared minus 1, I might be able to do something there because then it would be in the format for arc secant. Generally, when I start to feel like I'm cycling, but I'm not actually getting out of the spin and moving forward, that's when you have to back up and say, wait. Look, the degree of the bottom is 4, whereas the degree of the top is 1. And remember me telling you, when these are separated, when it's not just like 1 and 2 or 4 and 3, that tends to be a trigger that you need to consider the arc trig functions. Now, there is no one hard and fast rule, but I'm kind of trying to give you some ideas for when you switch your thinking from what your gut instinct is, which is to let the bottom or part of the bottom be u, to instead going, is this an arc trig thing? All right, so is it an arc trig thing? Could I make this x to the fourth something squared? Yes. X to the fourth is x squared squared. So if I wanted to get this into the 1 plus u squared format so I can make it arctan u, I would have to say, let me make u squared be x squared squared. That means u is just x squared. That means du equals 2x dx. Now I'm making progress. So I'm going to say this is 1. I'm going to move the x dx that I've not dealt with out here. So I still have to replace the x dx, and I can replace the x dx if I make it 1/2 du. Ah, now I've got it. I can make it 1/2 du. So again, you have to be on your toes, and once you see it, I think you'll be able to finish it. What we're talking about more is how do you even like come up with the idea to, could it be an arctan thing? That's the hard part, because now I can go, oh, okay, so this is arctan u. Wait a minute, u is x squared, so it's arctan x squared plus c. So once you get the idea to use arctan u, you're going to move a little more quickly. It's just getting that idea that's tough. All right, last but not least, these are two problems that I think are exceptionally difficult because neither one of them look like they're anywhere near being like 1 over u squared plus 1. Like I have no idea how I do either of those. But I do notice, I mean, they're definitely bottom heavy. The bottom degree is 2, whereas the top degree is 0. So I know there's something kind of fancy going on here. It's not your basic u sub problem. Because again, think about it. If you let u be the 9x squared plus 6x plus 1, then du would automatically be what, 18x plus 6 du? So I would need something with x's on the top, okay? Now again, this could possibly fall into the category of partial fraction decomposition, which is actually a Calc 2 topic. But if this problem is given in Calc 1, that means it's not partial fraction decomposition, but next year that's probably where you would head with it. So what I notice is, wait a minute, can't I factor this? So I notice that this factors into 3x plus 1 squared, because 3x squared is here, 9x squared. 3x times 1 is 3x, doubled is 6x, 1 squared's here. Now, that in itself takes a lot of being calm and recognizing, and that's not easy. So if I do this, notice it's in the form of just 1 over u squared, because I could let u be 3x plus 1. Du, since u is linear, du is just going to be 3 dx. So if I want du right here, just take the dx and say that's 1/3 du. Now you know how to do this one because this goes back to just the power rule, where you say, add the exponent, divide by the new exponent, and then clean this up, okay? So I know that you could clean that up. You could put the u on bottom, sub back in your x's. So that's a hard problem. But then I look at this one and I'm like, this doesn't factor. So what do I do if it doesn't factor? So to me, this is extremely difficult. And it helps to have seen this one first because that's what gave me the idea. I was thinking when I looked at this, that on this one, I could make it 9x squared plus 6x plus 1 dx. That's what I was thinking, and I thought, but that won't work. It actually does work. Because now, from my previous work, I can see that this part is 3x plus 1 squared plus 1 dx. And I'm still thinking, how do you do that? Oh, if I make this 1 over u squared plus 1, I can move forward with it. So we just saw that in this case, u would be 3x plus 1, du is 3dx, so this dx needs to get replaced with 1/3 du. That's a hard problem. That's an extremely hard problem. And so, of course, now I've got arctangent u plus c. Okay, so those are your arc trig problems. And then tomorrow, we're really going to work on mixing all of those and like what are little triggers in the problem that help you tell one, if you've got a fractional integrand, to tell kind of like what's your checklist. So you might try this first and try that second and try that third, because that's really what we need to get you to, is being able to mix these and recognize which one is which. But it's not easy, but we'll keep working together on it.